Imagine you have an infinitely large, incredibly thin sheet of paper, and it is uniformly covered in positive electric charge. Your goal is to find the exact electric field at some point hovering above it. If you try to do this the old-fashioned way, you have to imagine billions of tiny arrows from every single charge on the infinite sheet and add them all together using complex calculus. It is a nightmare. But there is a brilliant shortcut that completely bypasses the calculus. It is called Gauss's theorem. To understand Gauss's theorem, imagine a glowing light bulb trapped inside a box. The total amount of light piercing through the walls of the box depends only on how bright the bulb is inside. It does not matter if the box is a sphere, a cube, or a weird potato shape. The total light poking out is exactly the same. In physics, we call this poking out effect flux. Gauss's theorem says that the total electric flux piercing through any closed 3D surface is equal to the total charge trapped inside, divided by a constant called epsilon naught. To solve our infinite sheet problem, we really just need to do three things. First, figure out the symmetry of the field. Second, draw a clever 3D trap called a Gaussian surface. Third, calculate the flux. Let us start with step 1, symmetry. Imagine looking at this infinite wall of charge from the side. Could the electric field point outward at a diagonal angle? Pause here and predict what the field lines must look like. Because the sheet is infinite, for every charge pushing diagonally to the right, there is an identical charge perfectly balancing it by pushing to the left. The sideways forces completely cancel each other out. This means the electric field lines have no choice but to point straight out, perfectly perpendicular to the sheet. Now for step 2. We need to draw an imaginary 3D boundary to trap some of this charge. What kind of 3D shape perfectly aligns with these straight parallel field lines? Pause and think about what shape would make the math easiest. A simple cylinder, often called a Gaussian pillbox, is perfect. We position it so it pierces right through the sheet like a cookie cutter. Let us look closely at this cylinder. It has two flat circular caps, each with an area we will call A and a curved middle body. For step 3, we calculate the electric flux. Let us look at the curved body first. Do any electric field lines pierce through this curved side? Pause and look closely at the diagram. No, they do not. The field lines run perfectly parallel to the curved wall, sliding right past it. So the flux through the curved part is exactly 0. But look at the two flat caps. The field lines pierce straight through them, hitting them perfectly head-on. The flux through the right cap is simply the electric field E multiplied by the area. Since there is an identical cap on the left side, we get another E times A. Adding them together, our total flux is 2EA. Now we need the other side of Gauss's equation. How much charge did our imaginary cylinder actually trap inside? We are given the surface charge density, sigma, which is just the amount of charge per unit area. So the total trapped charge is simply sigma multiplied by the circular area that we sliced out. Now we bring back Gauss's master equation, total flux equals trapped charge over epsilon naught. Let us plug in the pieces we just found. 2EA equals sigma times A, all divided by epsilon naught. Watch what happens to the area A. It is on both sides of the equation, so it completely cancels out. If we rearrange what is left to solve for E, we get our final answer. The electric field E equals sigma divided by 2 epsilon naught. Let us do a quick sanity check. Look closely at this final formula. Do you notice what is missing? There is no letter R or D for distance. The electric field is exactly the same whether you are 1 millimeter away or 1 mile away. Why does that make sense? Because as you move further away, your field of view widens, exposing you to more of the infinite charge, which perfectly balances out the fact that you are further from the surface. You just used symmetry and Gauss's law to bypass an infinite calculus nightmare. You did not just solve one problem today. You learned a powerful pattern. Use symmetry to your advantage, pick a smart shape, and let the geometry do the heavy lifting.